In this video, we're going to take a step back and introduce another fluid property that we really have largely ignored up to this point and haven't even discussed, and that's vapor pressure. And the reason we want to discuss vapor pressure because it has a very important effect on what we call cavitation, which can be an extremely damaging problem, and it's especially important when we start talking about pump design and pump selection. So vapor pressure is a property of a fluid that if you had fluid in an enclosed vessel and pulled out all the air above it, such that it was a vacuum, eventually some of that fluid would evaporate and there would be an equilibrium pressure in that vacuum of molecules of water or whatever that fluid is. And the pressure that becomes at equilibrium is what we call the vapor pressure. And so basically what happens is that at any temperature, or if you have a fluid that the vapor pressure is equal to atmospheric pressure, it will boil. Okay? So vapor pressure is defined as the pressure that vapor exerts on a liquid surface at equilibrium in a vacuum. Vapor pressure is a unique property of a fluid that's determined by molecular activity and makeup, but it's also very dependent on temperature. In fact, I show here, this is a table out of your book, and here's the vapor pressure there in pounds per inch squared. We typically, again, vapor pressure always reported absolute pressure because it's usually relative to atmospheric, and we'll talk a little bit about that when we talk about boiling. And you can see that as you increase the temperature of the fluid, the vapor pressure also goes up. Okay? And that, again, is getting to the idea of boiling. So boiling occurs when the vapor pressure is equal to the local atmospheric pressure or pressure inside the vessel. So if you're heating something, the vapor pressure, it'll start to boil when the vapor pressure is equal to the pressure outside or in that vessel. So for example, the vapor pressure at 212 degrees Fahrenheit here is equal to 1.469 e to the 1, which is 14.7 psi. We have boiling. And so at at sea level, that's the case, and then as you increase elevation, the atmospheric pressure goes down, and so the PV can be lower, and that's why water boils at a lower temperature at higher elevation. Okay? So that's boiling. And the reason we care about vapor pressure for engineered system is that the local pressure in a piping system, whatever fluids in that piping system, or even an HVAC system, can be low enough that it's lower than the vapor pressure, and you can actually cause bubble formation and boiling within, say, a pump or within a pipe. So this can happen near a very tight fitting with the water going through the fitting, or it can happen when we have the impeller of a pump. And when that happens, these bubbles form in the flow, and those bubbles move along, and then we get cavitation. When the cavitation occurs, the pressure goes back up, then those bubbles dissolve back into the water, right? And when they dissolve back in, they collapse, and that can really cause some severe structural damage. It can absolutely destroy a pump or a piping system. And so we always want to be very, very careful that we don't hit any cavitation level. In fact, this is probably the most important thing when we're talking about pump design. Well, first is the pump has to be operational within our flow curves, but then the second thing would be the cavitation. And in a lot of cases, that's more important because if you have an undersized pump, it's generally not going to, the system's just not going to work. If you have a pump that's going to cavitate, you're going to destroy the pump and have to buy a new one. So again, these are two trade-offs in design that we have to deal with. And what you'll see often for pumping systems is we'll define something called the net positive suction head, and that is equal to the pressure at the suction over gamma plus V suction, the velocity at the inlet, over 2G minus the vapor pressure. So this is, again, PV is the vapor pressure. So that's the unit we just talked about. It is a property of the fluid, so you just plug it in for whatever fluid you're working with. And so that was, again, what we call the net positive suction head. And from an engineering standpoint, there's two values of net positive suction head that we're really interested in. One is the required net positive suction head, and that's in PSHR, so shown here. This is the required net positive suction head. And the required net positive suction head, what that is the head needed at the suction in the inlet of the pump in order for the pump to actually operate. Okay, and that's often a reported value. Okay, so this is the head required at the inlet for it to operate. And if it's below that, if the net positive suction head at the inlet is below that, then you'll get cavitation. So the next one we're interested in is the available. All right, so this is the available net positive suction head. So this is actually a property of the system that you've designed, and so this is the suction head that's available because of the system, and so it's going to be a result of atmospheric pressure if you're moving from the reservoir, atmospheric pressure plus some depth, plus change in elevation, plus the velocity head that's associated with that at the inlet. Okay, and generally speaking, in an engineered system, when you design, you want a situation where NPSHA is always greater than or equal to NPSHR to prevent cavitation. Okay, so that's vapor pressure and cavitation in a nutshell. Again, the main reason we care about it is because pumps themselves can cause cavitation if we aren't careful and don't design for this phenomenon. All right.